This will come up later today. This is a map of the world. It's a funny looking map of the world. Anyone notice anything funny about it? It's like Greenland is as big as South America. There's something that has to do with trigonometry that has to do with this map, and I knew about it and I looked it up, but I found out all sorts of neat things. This is called a Mercator projection. I don't think it was invented by Mr. Mercator. I don't know why it has that name. Maybe it was. Could be wrong. I also found out when I was in second grade or third grade, they had a map of this on the wall, and of course I got this wrong impression of the size of things. And in fact, I learned when I was reading Wikipedia that in fact map makers like 200 years ago started using this. And most people have a distorted view of the sizes of things because of this one map. So you might ask, well, why the heck do they have this map? And we're going to get to that later. There's actually a good reason for it. It's kind of neat. Okay, so Mercator. Everybody, I've emailed everybody, I mentioned it. There's a quiz on Thursday. It'll be mostly on section 8.4 and 8.5. It won't include anything we do today or tomorrow, or Thursday. Whatever homework you hand in, I will endeavor to get back to you, so you'll have, you can ask questions about the homework today, and when I hand it back, you'll have time to ask questions before the quiz. So I guess that's the next thing. Are there any questions about this homework that people would like?
Let's go over problem number 3. I don't know, problem 4C. I think my graph turned out a bit off. So
your question will hold for a minute, won't it?
And
which page? You want to tell me? There's 2 homeworks.
From on 8.4.
Okay, number 3.
Number 4.
Number 4. Answer all the following questions for each function. What is this? Period. This is the cosine of theta minus 120?
Yeah.
Okay, do you want me to go through everything on it?
No, just B.
What is the maximum?
My question, I think it turned out wrong, so that's why I wanted to go over it.
Okay, but is your question about what is the max and min values of f? That's B.
What? No, I'm talking about B.
Graph the function using a calculator. Make sure to graph at least one complete period. Okay, so let's see how we would do this. So they want you to plug in cosine of this case is x. Oh, before we do that, let's make sure my mode is in degrees. Sure. Cosine of x minus 220. The book says graph the function. Oh, without using a calculator. I'm sorry. I missed that all important word. Without. Okay. cosine, and there's no d value, there's no horizontal v, right? Yeah. There's no horizontal, there's no vertical offset, right? So the sine and cosine is going to go between 1 and -1. It's a good place to start. Just kind of give us some limits. The b value is 1. Right? That's not right? Let me write, I guess I should write this. Cosine of theta minus 120. So the b value is just 1. So that tells me the period is going to be period for just the regular old sine or cosine. 360 or 2 pi. We're going to do it in degrees since they gave it to us in degrees. So let's create some 30, 60, 90, 20, 50, 80, a lot more. 10, 40, 70, 200, 30. Maybe I should change my scale a bit. All right, we'll put it there for the moment. All right, so the only thing really left, we need to know kind of what a cosine looks like. Just the regular old cosine is going to look like this. That would be 360 degrees. We need to know where it starts. So that's the horizontal offset or the phase shift. So where is the cosine going to start? At 120. All right. So from 120 for 360 degrees, we're going to have to go a little further, right? 390. You don't actually have to draw the whole thing. You just want to draw one whole period, but 50 or 80. So from here to here is, as you say, my scale wasn't so good, but that's okay. So I want to break this up into quarters. So that's where kind of the 90-degree offset is. That's 180. Okay. So now I start up here. I come down here. Go back here. Yep. Oh, I'm going to be here. I'm going to come back here. Okay, now, you could kind of go back like that. I guess this is going to be the first thing. You might notice this is not the most artistic drawing. Some of you, no doubt, are better at it than I am. I'm just showing you my expectation is not that this is some masterpiece, just that it shows the important elements. You know, there's a maximum of 120, there's a minimum of 200, goes through 0 in these various places. Okay? Good? Okay. Your question? About 42? Okay, the same section? Sorry?
8.5 on page
8.5.
Okay.
8.5. Okay, so this is now we're into the modeling. And we have a big table here. There we go. Hours of daylight. The table displays the number of hours of daylight in Seattle, days after March 21st. So he's just setting his axis to be 0 at March 21st. Use the table to answer the following questions. Hint, be sure to use radian mode on your calculator. Okay.
The questions on the top, right?
Yeah, I'm gonna pull that down. So here are the questions. Find an equation for the sinusoidal function HD to model the number of daylight hours in Seattle. Okay, so this is something, we did something like this on last Thursday. To do this, we want to do it in a methodical manner. We want to get some basic information. So let's start with, what's the max value, the min value?
1598.
I'm just going to steal this. Oh, 1598. And the minimum was 843. So now the amplitude, A value, is just going to be 1598. What do we do with these two for the amplitude?
The difference divided by 2.
The difference over 2. Everybody here divide in their head like this?
What problem number is this again? What do you do? 178.
Yeah, it's section 8.5. This is we're modeling the number of daylight hours in Seattle, Washington. All right, so that's our amplitude, about 3.77. Our midline, right? Midline is what? Well, we add these two. 1598 and 843 and divide by 2. Okay, let's see. So that's just going to be 1624.41 over 2 is going to be 12.205. We don't really have. Okay, so that's our midline, and that's our midline. That's the D, right? All right. Now we want to figure out the period. Right? The period is going to help us. I guess I should write this. This could be sine or cosine, but a sine of d x minus beta minus c plus d. So we've got a and d. We want to find d, so we want to find the period. So we have to look at these numbers. Well, it peaks around 90. We can't really see, we don't have enough data, do we? We get the other peak. It's kind of a problem, isn't it?
Kind of looks like it's about the end of it. But
Well, it gets down to 1188. Right? Let's just see what, let's just take a look at this. Now, this is kind of good if you're in a, I don't know, in a science class and like real data points, you know, unlike an applied math class or this class, which is not, I guess, this sort of applied. All right, what's happening here? See this? It's going down, I'm sorry, it's going up, peaks, starts going down again, and it hits the bottom, and now it's kind of going up again. So we don't really know, but it looks like 11.88 is pretty close to 12.20. Maybe.
So it's like the next point would probably be about 12.
Yeah. Now we can also be kind of smart about this. This is days, right, after a certain day. So 0, 30, or 360. 365 is just going to get us right back there again, isn't it? I mean, of course, this is about the Earth going around the sun and how many daylight hours we get. The period has to be, you didn't really have to look at the data, you could just use your brain and say, the period has to be how many days? 365, right. So if the period is 365. That's equal to what? Pi in radians over the absolute value of b. Well, these are positive, you don't have to worry about absolute value. So b is pi over 365. And, you know, again, in a real sciencey kind of way, you could simplify this into a number, but let's leave it that way for the moment. Right? It might be useful to delay figuring this out. Okay, so we have almost everything we need. The only thing we don't know is where the darn thing begins and ends, right? We know sine wave kind of looks like this, and then it keeps going on, but that's where it starts. This is 0. And we know a cosine kind of goes like this. It's the same shape, it's just offset. So, you could use your imagination here a little. I'm not going to. And you could say, do I want a sine or a cosine? But, well, I'm not gonna judge that. I'm just gonna look at this and go, what point is it close to the midline? Close to midline, 12.2, and starting to move up.
You can technically use either, right?
Oh, that's right there. At 0. That sounds like a sine, doesn't it? It doesn't sound like a sine, it sounds like a sine with an offset of 0. So we can model this function as 3.77 times the sine of b, which I'm just going to leave it this way. If we have to calculate anything, the calculator is kind of better than we are, times x minus c, which is 0, plus 12.2. Now, it might not hurt to do a sanity check here. Let's just plug in 0. Sine of 0 is 0. This is 0, 12.2. Yeah, that's at least the first point we got right. You might want to try one more point for a sanity check. I'm not going to do that, because I know it's right. Okay, so that was A. I'll let you ask your question. I just want to say, and I think that was the hard part, doing all that work. Right? Now we've got a good model for this. Yes?
For the period, is it 2 pi over b or is it pi over b?
Forget.
It's 2 pi.
Oh.
Because of polarization.
Oh yeah. That's right. That's right. Thank you. Not infallible up here.
I was just a little confused because I thought you got pi from something else. I missed something.
Okay. All right. Do I have it right now?
I don't know. I was confused where you got the pi from. That's all.
Where do I get the pi from?
No. I know where it comes from. I was.
Oh, why didn't it have a 2 in front of it? Is that?
Yeah, absolutely.
Yeah. Well, you were right to be confused. Don't you see? Now you should. Everybody, it's a lesson here.
So in your formula,
Just because the teacher's up here saying something, if it doesn't look right, it doesn't mean you're crazy, right? Yes.
So I rounded 2 pi over 365 to be 1. I know it's not. If you did it on the test, we get B.
Wait. It should be near 1, actually.
Wait a minute. Say it again.
So I know it's 2 pi over 360 is equal to 1. So I just eyeballed it and rounded it. And 2 pi over 365 is 1. Even though I know it's not. It's very close.
Wait. Pi is 3.1415, whatever. So 2 times 6 point something.
Talking about 2 pi radians.
Yeah, but for your...
Yeah, 2 pi radians is 6 point whatever radians. I agree with you. This is actually, it's kind of a, see, this is radians, and this is days per cycle, right? So if you ignore, if you adjusted the units to be the same, and they drop out, you get 1. This is a name for 1, I agree. But right now, we want these units in here because our x-axis is not in degrees or radians, it's in days. Right? There's 365 days in the cycle, so it's a little different unit. There's some irony there, since probably the reason we have 360 degrees in a circle probably has something to do with the fact that we have close to 360 days in a year. Okay. You need me to do, you want me to go on, right? Okay, use this function to estimate when the number of daylight hours will be 13 hours. Oh, so we want this to be equal to 13. Yeah, you know, the funny thing about this is,
So that's what I basically do. I don't know if
this is a funny book because the straightforward way to do this is you solve for x, and to do that you need to know the inverse sine function, something we haven't covered yet. There's a button on your calculator if you want to be smart and go do that. So I was going to try and, you know, provide a way to do it without doing that, which would be you look at the table and you say, well, where's 13? It's between 0 and 30. And then you can kind of plug in some numbers. You know, in other words, if you can plug in 15 here, and you know, you can kind of jog back and forth and get 13. But
You get some answers, right? Because it's a problem at that point.
if you say, I thought I heard you say parabola, which I don't think is what you meant.
Well, it's captured with 365, it goes.
So, you're talking about here and here. Yes, that's right.
Everything else.
That's right.
So all I did was I got my equation, and then I drew it on my calculator, and I then underneath that I put y equals 13, and I just saw what the intercept.
Oh, that's right. You got it on your calculator. Does everybody know what somebody want to see me do that? Okay. Because this is fun. I think this is fun.
I got it very quick.
We couldn't do this when I was in school. All right, I'm gonna do 3.77 sine of 2 times pi. I'm just gonna put x in here. Times x divided by 365 plus 12.2. Unfortunately, I think my...
No, you wanted to zoom?
Yeah, I realized that. I didn't show up. Just to show everybody, this is just what I typed in here. And I want to say, what, zoom...
0.
Zoom 0?
Yeah. No, keep going down. Or just say 0.
Oh, zoom fit. That's what I was thinking of. Okay, so... This doesn't look good at all. I don't think that's what we want.
Look, it's a line.
I think it's only one, but just kind of say.
I don't actually have to get the graph. So this is between 3.77 and negative 3.7. So let me look at my window. Okay, that part of it's okay. The problem is the y's. And I'm sorry. Let's just say 4. Wait. Oh, I see. 12 plus or minus 4, right? So 16. I want the y, top y to be 16, make it 17. The bottom to be 6. Okay. And now I want in 0 and 365.
y min 17, y max 6.
Oh, I got in reverse, don't I?
So y min is 6. Y max is 17.
Oh, 6. Thank you. That doesn't look any better, does it?
Well, if it's on the if it's on the step, not step, if it's on the edit thing, you can do zoom step. Because you have it all written down. You just scroll down to zoom step. Right there, number 9.
Zoom stat.
Yeah.
Oh, I've never used that before. Does that help? No.
It's just there.
Yeah,
So
so,
could you show us the numbers on the problem on the
yeah, I don't think.
If you solve for 13, you get like a pretty solid number. It's like 120.
What was the minimum here that you find? It's like 8. And the maximum was 16. And maybe my function isn't right. I'm beginning to think I have to go with my function again. Maybe I did something wrong when I entered it. That's entirely possible. So I've got the A correct, and I have 2 pi times x divided by remember pi times x plus 12.2.
You're usually do sign question. Does it calculate and be means?
Oh! I don't know.
Because of that too.
Yeah, there we go. Thank you. Somebody knows. It's so lovely. Okay, so now, here's something, now that we finally got what we were beating our heads against. Let's put in another y equals.
You can't see.
They can't see the
There you go.
Sorry,
That's what I got to.
you can see it better up there than I can see over here. So we're going to add in another function. Y equals, what was the number they were looking for? 13. Oh, yay! Okay, so now these calculators do something fabulous here.
So this is the tricky part.
Yes.
What is your x-axis? What is it in?
Days.
It's in days. So you get, I did some funny conversions with that, right? I'm just curious as what you were going to call it.
It's in days, but the function up there, the input to the sign is in radians. That's what this thing does. We could have made this 360 over 365 and then it would degrees. All right, so we're almost there. We've got 2 functions. We want to find their intersection. So there's a function called calculate, and we want to say intersection. Now, there are 2 intersections, right? It'll find this thing for us, but we've got to help it along a little. So let's say we want to find that first one. So we're just going to kind of put this here. We're going to enter, and what does he come up with? Well, 11.64. So 11 days in is where it's 13, or you can kind of, somebody see that little wandering intersection? Or we can put it near here and hit enter, and it's going to tell us at 174 days.
It actually hasn't calculated it yet.
Hasn't?
What you do is you start
Right.
with this curve and then
170, thank you.
no, now it's
It's a running line.
They found out where the 2 intersect.
Yeah, so we do 15 days?
what it wanted you to do. It wanted you to select first line and then the second line. The two graphs.
Yeah.
That you were finding intersection between.
So you have,
This is at the intersection, this intersection. There's two intersections, here and here. So all I did is I used the fact that I know it's going to find the intersection by jogging back and forth, and I put it close, and I said, go calculate it, and now we're here at 170. If I want to find the other one, just want to steer my x over here, hit enter.
I think you have to
Oh, you have to do that again? Okay. Intersect. Yeah, you're right. Not as smart as I thought. I mean, I could start checking from here, a little further away, but it would take longer. Okay, there we go. Again, 15 and a half days.
Well, you need the second curve.
Hmm?
You still need to select the second curve, yes.
yeah, see, you press one more time. There you go. That's
Oh,
how you get it.
sorry. 12.4. I guess it's embarrassing. I'm not expert with the calculator. I should be. Just an expert with the math. Okay. All right. That was part B, right? And then finally we have what is the average rate of change from d equals 30 to d equals 120. Rate of change. So we're talking picking some point here and another point here. 30, the value is what? Go back to the numbers. 30, it's 1407. Right up here. 30 is 1407, and 120.
15.53.
Say again, 15.
15.53.
So rate, right? Slope of the, if you have a linear curve, it's the slope of the curve, rate of change. We want the rate of change, you know, delta y over delta x, right? And this is a curve, but we just want the average. So the rate of change is going to be, delta y is going to be 15.53 minus 14.07 over 120 minus 30, which is 1.46 over 90, which is a nice number to throw in your calculator. In other words, now it helps with this problem because it's a nice, we know this problem. Every day from now until June, days get a little longer. They got shorter until December 21st, the solstice. And so he's saying from 30 days after, whatever the date here was, March, he started, what's the average rate? In other words, how much does a day change in that period? It changes not much. Number of daylight hours. So 90 over, that's just like moving the decimal point over 2 places. 0.1 hour, 0.01 hour, that's about a minute. Yeah. If you think about it,
It wants it as a percentage, right?
oh, multiply 500. So 1%, about 1%. Well, the better number, but about, it's a little more than 1%. You know, right here at the, oh gosh, I should know this stuff. The equinox, the slope of the line is kind of at its greatest, and it's changing the fastest. Up here at the solstice, it's changing the slowest, and now here it's changing the fastest again, but it's going downhill. So, in winter or in summer, the numbers change slowly, and then right in the middle they change fast. Yes. I feel like this is a science class. We're learning about the sun going through the sun. This is trig, right? Yeah.
Maybe I didn't that one, but I missed why you wanted to the whole process.
Because he said they asked for it as a percentage,
Oh,
right? I hope that is clear.
yeah.
Okay. All right, are there other questions on this homework?
I didn't understand number 2 on the homework sheet, and I'm wondering if I used the graphs properly on number 3.
Okay, when you say the homework sheet, you mean the in-class sheet?
Yeah.
Write 5 different angles that are equal to the reference angle.
What does that mean?
Okay. Surely it wouldn't hurt for us to revisit the reference angle. So, if you have, I have yours, you need it? Okay. If you have an angle in the first quadrant, some theta, it is a reference angle. Reference angles are between 0 and pi over 2 or 90 degrees. Now, if this is a reference angle, then if you draw a horizontal line over here, if you think about it, the coordinates of this point on the unit circle are cosine of theta and sine of theta. And for this angle, which is over here, which is its supplement, the lengths of these two sides are the same, and these two are the same, which means that you also have cosine theta and sine theta, except that one of these is negative. Right? These are both positive. And here, the same numbers, which is which? Cosine is negative. We come down to a point here. Well, I didn't draw that right. We're both negative. And same point here, in other words, this is theta, this is theta, this is theta. We now have positive and negative. So all 4 of these angles have the same reference angle. We can use the reference angle, find the sine and cosine, and then we just have to adjust the negative positive sign in the front of it. So what 2 is asking is, I'm going to give you an angle, and I want 5 more angles that have the same reference angle. Now, you can be really, really sloppy with this, right? You could say, well, 55 degrees plus 360 degrees is 415 degrees. That's an angle that goes all the way around and comes back. It's the same angle, but it's a different number. But clearly, it has the same reference angle. There aren't just 4 reference angles. There's 5, there's 6, there's an infinite number. So again, you can be really sloppy, and you can say, well, that's one of them. Add 360 to that, and that would be, right, that's another one. You can keep doing that. Or, oh look, you could just add 180 and you get this one. Or you could find the supplement of this. Subtract this from 180 and that would be 125. So really, I just want you to feel a little comfortable with this idea of a reference angle.
Okay, so it's just basically you just constantly add 362 to
That's a cheap way to answer the question, yes. But all four of these, angles, and each of those angles plus 360 is the same reference angle as this theta here.
Yeah. By the way, we add like when if it equals the same thing, can we also add that? Like for example, if the 180 is the same, amount to the same amount.
I didn't understand the question.
Never mind. I just answered it because it wasn't sine or cosine, but no, that wouldn't work. So never mind.
All right, any other homework questions before we move on?
I was double checking the graph to make on number 3 of it too. I don't know.
Jonathan, do you mind if I use your graph here? You mean this?
Oh.
Now I don't mean to use your example here. It does look like it's not quite a sine function. I think I know what you meant. You kind of meant something that kind of goes up and down, up and down, right? Yeah, okay, a little softer curve on the bottom there. You have a question about this one?
That looks like.
I graphed it wrong.
Okay. All right. Any other questions? Okay. Before we get into the other trig functions, which are the subject for today, the new subject, I just want to point out something that whether we talk about something being, we have a definition of what the sine and cosine function are. But if we graph them, if we graph the sine and cosine function, they really look pretty much the same, except that there's a horizontal offset. So in this particular example, I show you here that the sine is the same as the cosine if you just add 3 pi over 2. Your C value, your horizontal offset is negative 3 pi over 2. And on top of that, let me be clear about this notation here. So I had, say, 2 pi plus 2 pi n. And then I say, you probably aren't familiar with this symbol here. Does anyone know what this symbol is? It's a set thing, but it means member of, and I have in squiggly brackets a set. So the set I'm trying to describe here is the integers. So if n is an integer, then 2 pi n is either 0 or 2 pi or 4 pi or negative 2 pi. You can add those values in here because it's periodic, because that's the period. It doesn't change anything. So again, I just want to be clear. There's really only one fundamentally new function here. We just have the sine and cosine are kind of the same, but offset in the x direction. So now we're going to talk about some new functions that we can construct with the sine and cosine. The first one is called the tangent function. I think the term has come up earlier, and I think I cautioned you not to draw any similarity between this term and the other use of tangent you should all know. Right? What's a tangent? Does everyone remember what the angle that the tangent of the circle makes with the radius? Yeah, it's always a 90 degree. For those of you who go on to calculus after this, you're going to find that any old curve could also have that kind of tangent. Although we have to come up with a good definition of what that is. We're not going to do here. But this is not the tangent we're talking about. I guess it's a straight line and it has a slope, but I don't see any connection.
Quick question about this function here. So it's cosine of x plus 3 pi plus 2 pi and close parentheses multiplied by n? Or is that just to define what?
2 pi times n, yeah.
No, but I mean the part right after. Right after the parentheses close. Is that multiplying by n?
No. This is just, maybe I should put a comma in there.
Okay.
I'm just identifying, what does this n mean? N is could be any member of this set of integers. Okay, so we have this new function, tangent, which we define as sine over the cosine. And I'm just going to go through these real quick. We're going to discuss them and find out all about these functions. We have a function called the, and I also want to make clear, this is the standard abbreviation for tangent we use, tangent function. Cotangent, for some odd reason, people differ. Some call it the cot, and someone called it kitten, CTN. Either is fine, it doesn't matter, as long as you know what's going on. They're both the same. The cotangent is going to be the reciprocal of the tangent. It's going to be, instead of the sine over the cosine, it's going to be the cosine over the sine. And then we have two more functions. Here again, we borrow a term from geometry, a secant. In geometry means something totally different. Anyone remember what a secant is in geometry? Just a line segment connecting two points on a circle. The diameter is a secant. We just don't call it a secant, we call it diameter. No, that one isn't, but
if you drew, the one you drew wasn't, but that is,
This is a secant that is also a diameter. This is not the same secant. And it's defined as 1 over the cosine. Now, I think when people made these up, you would think, why can't it just be logical? Secant is 1 over the sine, the cosecant is 1 over the cosine. But it's not. So you just have to remember, secant 1 over cosine, cosecant 1 over sine. And you do want to remember these. We're going to talk about these now. Altogether, these are the 6 trig functions. So let's take a look at the tangent function for a second. Here's all focus. Let's first think about this for a second. This is not quite as nice as the sine and cosine because it's not defined everywhere, is it? Where would it not be defined?
Cosine equals 0?
when the cosine equals 0. Yeah. Where does the cosine equal 0?
Basically, whenever it's 180 degrees or 180.
Pi over 2
Zero,
plus k
or-
pi such that k is an integer.
Pi
Or 2 pi.
plus 2 pi n
Yeah.
plus 2 pi n. There. And just remember, okay, we're going to abbreviate that set.
So can we just say
Integers.
0 plus pi?
We're going to do this very high-level math here.
Instead of having 2, can't we just do 0 plus pi n? Instead of 2 pi n?
Ooh. Okay, now we have simplification.
Or 0 plus pi n.
What is pi n? Is that what you meant?
Oh, pi n is what,
Yeah, that works.
Cosine 0 at 90 degrees, not 20.
no, sine is 0 at 90 degrees.
All right, let's just draw the unit circle here. Cosine 0, cosine 0. It's a good image to put in your head. Okay, so it's not defined there. What's going to happen when we get really close to these points here? What's going to happen to sine of, say, x over cosine of x? Cosine gets really, really close to 0. It's going to get really small, right? And if you divide something by something really small, it's going to get really big or maybe really negative. Well, okay, let's take a look. So this is the graph of the tangent. Now, one thing to notice is it's periodic, right? Just like sine and cosine. But when you get close to pi and negative pi here, or 2 pi over here, what happens? Well, when sine and cosine are both the same plus or minus sign, they're both negative, the negatives cancel out, it goes very high. As you get close from the other direction, one of them is positive, one of them is negative, it gets very large in a negative sense. I don't want to say very small, because to be small means very close to 0. All right, so you'll notice that there, oh, I guess you can't see it very well, there are supposedly dashed lines here that the function gets very, very close to, kind of stuck between them, but it gets closer and closer and closer. Does anyone know what those lines are called? Asymptotes. I'm going to push this up a little because I'm not a very good speller. A-S-Y-M-P-T-O-T-E-S. So, an asymptote is just a straight line that some function gets closer and closer and closer to. It never gets there. These are vertical asymptotes, and you'll see that they appear periodically. All right? They certainly appear at pi over 2 and negative pi over 2. And then they appear periodically at the period of this function, which we're going to talk about in a second. Right? So, all right, I have some questions here. We already talked about where is it not defined. What is its period? Can anybody looking just at this, kind of eyeball it and see what the period is? remember these asymptotes are at negative pi and pi over 2, and it fits between them, right? And it repeats.
So kind of
Yeah, so it's just pi. Now this is different from sine and cosine, right? Sine and cosine is 2 pi. We want to keep that in mind. Okay, let's ask some real mathy questions here. What is the domain of this function? Well, clearly, almost. It's not all real numbers. Oh, I'm going to use a. Have you seen this notation? Or a big fancy R. It's all real numbers, but not. And I'm going to just say things that are not part of the real numbers.
Did you just do the
Well-
not sign as epsilon with the cross grid?
I'm sorry?
Did you use the not sign as epsilon with the cross grid?
Yes.
Okay.
It's actually not an.
Not an epsilon?
Yeah, an epsilon is kind of like this. And this symbol is kind of like this.
I see what you mean.
I appreciate you guys showing me the humor in this. It is funny.
Very well, very well.
Epsilon is a Greek letter. This thing is a mathematical symbol. They do a lot, especially when I write them. If I have some font here that shows you the difference, I'll gladly do that. Okay, so my symbol is the not member of what? Pi over 2 plus 2 pi n, and negative pi over 2 plus 2 pi n, right? In other words, our domain is defined everywhere. So I can use a pointer here, except, that's how I do it, except where these asymptotes are, right? Asymptotes. I don't know if I pronounce it like that right all the time. The point where the function goes off to infinity. That's not part of the domain. Okay, how about the range? Range. What's the range of this function? It is all real numbers. You get any real number you want from the tangent function, yes.
For the domain, is there a way of saying if that's tangent, basically excluding, basically it's for all real numbers except for which cosine of x equals 0, I think?
I'm just creating some room for what he said, what he was trying to say. He was saying real numbers, actually he would say
shouldn't the domain be
real numbers excluding the set where cosine of x is equal to 0.
for the domain?
Is that what you meant?
Yeah.
Yeah, that's good.
For the,
Okay.
for the
That's-
domain,
Yeah,
the
yes.
person drew out, instead of writing 2, could we just write pi over 2 plus pi n, and wouldn't that cover them all?
Yes. He said, can I just say, excluding x such that x is equal to pi over 2 plus pi n, yes. There's a reason I'm not doing that, like, you're right, and it's better, actually, what you're saying than what I was saying. The reason I'm not jumping to that knee-jerk reaction is I keep thinking 2 pi periodicity, right? But you're quite right. Quite right. Okay, what is the function's amplitude?
There is none, is there?
No, there's no real amplitude. Now, you know, when we write this, just like we did with sine and cosine, you could put an a in front of it. figure out that number, but I don't know quite what we're going to call it. We're going to call it the amplitude. It's not really an amplitude. This function, I think this is a good moment for this little sidebar here. I want to talk for a second about something called an interval, right? Domains and ranges sometimes are intervals. What's an interval? Well, and some of you may have seen some of this before. So if I wanted to say all the real numbers between 1 and 2, including 1 and 2, I would write it this way with square brackets. Square brackets mean I include the 2. This is called an interval. I could also say all the real numbers between 1 and 2, but I don't include 1 and 2. The former is called a closed interval. This one is called an open interval. Anyone seen something like this before? In geometry, we sometimes will draw a line segment. We'll put a little circle at the end. Right? We don't really mean it has a fat endpoint. We mean we're not interested in the endpoint. It's not part of the line segment. It's the same idea. This is, think of this as like a real number line, 0, 1, 2. This is just an interval between these 2 points. It's open, meaning we don't include the endpoints. All right, I think the reason I wanted to include that here is because we have a way of writing, not the amplitude here, but the range. We could write the range this way. We could say it's from negative infinity to positive infinity. When an interval goes to infinity, we write it as an open interval, not a closed interval. And you also can have half open, half closed intervals. You could say like from 1 to 3, but you don't include 3, but you do include 1. Or, it could go from 1 to positive infinity. That would be another interval. So these are useful. It's another way of writing say 1 to 2. I could just as well say, x such that x is greater than or equal to 1 and less than or equal to 2. If it was an open interval, say x such that x is greater than 1 and less than 2. So these are just different, this is just mathematical notation. If you go on in math, you run into this stuff all the time and it'll come to you.
That's basically saying even between 1 and 2, that's greater than 0.
Well, in this case, it doesn't include 1 and 2,
Well,
and in this it does.
Yeah.
Yeah, it doesn't include 1 and 2, yes. I've also kind of thrown in a little notation. Sometimes we create like set notation here, and sometimes we use a colon. And for reasons I don't know, sometimes we use a vertical bar. They mean the same thing. When you see this colon or vertical bar, you say x, put in the words such that. X such that x is between 1 and 2. And again, these are all, you can write it using this interval notation too. I mention all this because we're gonna do a little of this now, somewhere along. Okay. I'm sorry.
Let's take a break.
7:05.
Oh, thank you. That's a good idea. Let's go over the tangent again. This is a graph. I want to back off a little. has vertical asymptotes. It's not defined where cosine is 0. This period is pi. The domain is the real numbers where cosine is not 0, which I have to correct. This is correct. It's pi over 2 plus 2 pi n and negative pi over 2 plus 2 pi n. Right? That's where the cosine is 0. Okay. Its range is all real numbers, and we don't really have an amplitude because it goes off to infinity. Okay. The next function we're going to look at very quickly, because it's just like the tangent function except it's reciprocal, is the cotangent. And most of the questions we asked about the tangent are just going to show up right away. So, what does the graph look like? Ooh, it looks an awful lot like the tangent function, except that instead of the tangent function, I'll just draw it in here. Tangent function kind of looks like this. It has asymptotes in a different place. It has an asymptote at 0, and then at pi, and negative pi. Where is it not defined? It's not defined where sine is equal to 0. So that's 0, and pi, and 2 pi, and negative pi. What's its period? Anybody? It's the same. The same. Same was pi. And I guess we just talked about its domain, so where sine is not equal to 0. These two questions are kind of the same, aren't they, if you think about it? And its range, what's its range? All real numbers. Again, it's just the reciprocal of the tangent, so it's very similar. Okay. So now we get into these two other elusive functions, which in a way are going to remind you, some of it's going to remind you a little of the sine and cosine, but it's going to be a little different. So here's the graph of the secant function, and I want to show you kind of how I come up with this. You'll notice in here, in kind of a dotted line, I have the cosine function. Since this is just 1 over the cosine function, I just can look at each point on the cosine and say, all right, here 1, what's the reciprocal of 1? Well, it's 1, so they coincide. As the cosine goes down, 1 over, it's going to go up. And as it gets down to 0, that's when the function goes flying up to infinity. Cosine function is symmetric across this axis, so it's going to look the same in this direction. Similarly, when you get down to this portion of the sine, you're going to have the same kind of shape, except turned over. It's going to go from -1 down to minus infinity. All right, so that's what the graph looks like. Let's look at these questions again. Where is the function not defined? Where cosine is 0. Which actually sounds like another function, doesn't it? That's the same thing as the tangent, right? So again, we have exactly the same set of horizontal asymptotes for this function. The function looks different, but the same asymptotes. Where are those asymptotes? Well, they're where cosine is 0. Simple. What is the period of this function? Well, we could do a little generalization here for a second. Let's say I have some function f of x, which is periodic with period e. That means that f of x is equal to f of x plus p for all x members of the domain, right, of f. Well, let's say I create a new function, g of x equals to 1 over f of x. So my question is, what does 1 over f of x plus p have to be equal to? Well, f of x plus p, we know what that is. It's the same as x. So this tells me that g of x plus p has to equal g of x. Okay, that's so sloppy, I'm going to do it again nicely here. I want to know what g of x plus p is, right? By definition, it's f of x plus p, which I know because the periodicity of f of x is 1 over x. So it's g of x. So I just showed that g of x plus p is g of x. What does that mean about g? It's a periodic function with period p, right? Okay. For those of you who are lost in the abstraction, don't panic. All I'm saying is, what I'm doing here, I'm kind of showing a very simple proof that if cosine of x has a period of 2 pi, 1 over cosine of x must have a period of 2 pi. That's all. Simple. Okay. So its period is 2 pi. Now, put on our thinking caps, what is its domain? Kind of answered that already. Thank you. Real numbers where x is not a member of x such that cosine. That's just a nice ugly way of writing it. Yeah, everywhere that the cosine is not 0, its domain. Now its range. Now this is another issue. What is its range? That's right, Aaron. Everyone hear him? From 1 to infinity, it goes up that way, includes this, and from there down also. We could write it this way. We could say the open interval from negative infinity to negative 1 and from 1 to infinity. Okay, we're going to close the loop here. We just have one more function. This is the cosecant, abbreviation CSC, which is defined as 1 over the sine. And just as the sine looks just like the cosine except switched over a little bit, you can see from the graph that this looks just like, cosecant looks just like the secant except moved over. And again, a nice way to graph this is to first draw in the sine function and then draw its reciprocal. And you see there are these asymptotes here. They're now at a different location because sine of x is 0 at a different place than cosine of x. All right, so I don't think we have to belabor this. Where is it not defined? Where sine of x equals 0. Where are the vertical asymptotes? Well, if you look, they're at 0, pi, 2 pi, 3 pi. And what is its period? Everybody should know this without even thinking. It's 2 pi. Again, it's the reciprocal of the periodic function. Its period is 2 pi. Its domain, we've already kind of gotten out. It's wherever sine is not 0. And the range, same as the cosine. Okay. All right. Kind of dragged ourselves through that. Let me just go back here and remind you, we now have 4 new functions to add to our list. They're not totally totally different. They're a little different from the sine and cosine. They're made up of the sine and cosine. But we're going to need to know all 4 of these and their properties. Okay, we're going to look at 1 or 2 more things here that are kind of easy and neat and useful. One of them you need to know, and the rest you don't need to know. This is the one you need to know. Think for a minute about if you have a linear equation. I just made one up, nice easy one. F of x equals 2x. And that's this thick line I drew here. And now we pick some point on it. And we draw a triangle, right? And it's a right triangle. So relative to this angle here, which kind of looks like one of our unit circle angles, except I'm not using a unit circle. And think about there being a circle of radius h over here. And let's take a look at this. So the sine of this angle is the opposite over the hypotenuse, right? Cosine is the adjacent over the hypotenuse. So the tangent, which is the sine over the cosine, the opposite over the hypotenuse, over the adjacent over the hypotenuse, is the opposite over the adjacent. I think we talked about this feature of the tangent before. Now I want you to notice something, remind you of something that you did in algebra or advanced algebra. Notice that in this diagram here, you can think of the opposite as a change in y and the adjacent as a change in x. change in y, delta y over delta x. You remember that from algebra? That's the opposite over the adjacent, that's the tangent. Well, what's that name we used in algebra for the change in y over change in x? The slope. The slope. So now, whenever we see a line in, I guess I didn't write this here, y equals mx plus b form. Everybody remember this? M being the slope, what's b? Y-intercept. We know something new that we didn't know before about m. M is the tangent of the angle that straight line makes with the x-axis. This can be useful information, right? This is a nice property of the tangent. Okay, that you need to know. I'm sorry. I just want to say a little bit about graphing here very quickly. Graphing these other four functions is pretty much the same as graphing the sine and cosine, right? You have, that same function. Let's say f of x equals a. We're just going to say tangent of b times x minus c plus d. For the most part, a, b, c, and d do the same thing. D is still a vertical shift, of course. It's true of any function, actually, but certainly true of these. C is just a horizontal shift where it starts. Now I'm actually feeling stupid. I keep making this mistake, don't I? P is 2 pi over the absolute value of b. The period is the same. We find the period the same. But something funny happens with A. Somebody asked me about this earlier during the break. Well, A is called the amplitude, but in this example where I say 2 tan of x, what happens? I have both tangent and 2 tangent graph here. You'll see that what happens is it's basically the same kind of shape. This one is the tangent. This one is 2 tangents. In other words, each point on here, it's multiplied by 2. This is negative, so they all come down. Here they all go up. So it kind of changes the severity of this shape. But it doesn't really change the overall idea. It's still going up to infinity. It's still going down to infinity. It's actually hard to draw these by hand and make them accurate. So don't feel like that's going to be not going to be one of the skills I'm going to expect out of you. But okay, so this is just a shortcut here, but keep that in mind when you're graphing these. The A, B, C, and D mostly do the same thing, except for the A. It does something a little different. All right. I think I promised you earlier that I'd talk about this Mercator projection. And this is definitely not on the quiz or the test or the final. I just think this is kind of fun. Let's see, did I lose it? No, I don't have it on my computer anymore. So the first question is, why Mercator projection? If it's so distorted, and why would anybody want to use this? Well, let's say you're a sailor. And let's say you want to plot a course, let's say from over here on the west coast of Australia to you want to go to the tip of India, right? So get out your map and you draw a line, and you know, you have an angle here too, right? I mean, you're out on the ocean and you can kind of figure out where north is and what angle do I travel at? Well, with any other projection, going from here to here is not a straight line on your map.
It's a curve.
It's a curve, okay? Which is awful inconvenient because you don't really know what the curve looks like. You just know it's a curve. Actually, if you're going from here to here, well, it's a curve too. I guess if you're on the equator, then it's a straight line. Or if you're going straight north-south on a longitude, it's a straight line. But otherwise, it's not, unless you happen to be fortunate to have a Mercator projection map. Okay, so, how do you make a Mercator projection map? What's the secret? Well, here we have 0 degrees, right? That's the equator. And I'm assuming this is going to go to 90, so this is probably 20 degrees, 40 degrees, 60, 80. You notice these are changing, the distance between them is changing. The way you plot this is instead of plotting this 20, 40, 60, 80, you stretch this by tangent function. It turns out, if you do that, well, tangent is 0, 0. You get a Mercator projection. Now, this answers a very simple question. Why is 90 not on the map? 90 would be what? That would be the North Pole, or negative 90 down here would be the South Pole. Why is that not on the map?
It's 90, it's 0.
Tangent of 90 is not 0. The tangent of 0 is 0. Tangent of 90 is...
Oh, sorry.
Negative 1, negative 2, approximately negative 2.
No.
Tangent of 90 would be 5.
Tangent of 90 would be the sine of 90 over the cosine of 90. The sine of 90 is 1. The cosine of 90 is... Oh. You need a map that goes off to infinity to include the pole. Yeah. So that's why you never see the poles on a Mercator projection. You can't fit it. All right, I just thought this is the coolest thing from trigonometry that I ran into. So, all you sailors out there, you all right. Okay, we have about half an hour left, and of course, I have a short little handout for you to spend a little time practicing with these new functions. There's a table. All the values in the table are exact. You want to check on your calculator. That's fine.
So for the homework, isn't this worksheet and then equal sorted by it?
Oh, I'm going to tell you about the homework in a second. Are you talking about the homework that's due today? Or?
Yes.
Oh, that was, like, I don't have it out off the top of my head.
8.4, 5.
Yeah. Yes, there's some homework for next Thursday that you could work on. out to me that my notes for the class today are not visible on the website yet. They're not. I will fix that. It's a typo problem. You can check. This is the homework for today that is due next Thursday. Of course. Again, as always, this is available on the website. Don't look at this yet, unless you want. And please begin. Okay. 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 But you know, the C here is negative 5. Yeah, that's essentially right.
So how do you the shift? So I know when there's a number in here, I'm supposed to like pull it out, right? I'm supposed to.
No. No. This is a function. Yeah. Some functions you can do that with. Right? Not with this one.
Here, I'll do one that threw me off. Threw me off. I had 7.
But again,
Well, that's different.
And I had 7x. 7. So when I got this, I thought the shift was to the right 7, but it's not, it's to the right 1.
Correct.
So when I see this,
I made a big deal about the fact that the form is A sine B x minus C plus B. I made a big deal about how it's not BX minus C, because then C does not have that nice property we want, which is shift.
so I do need to.
You have to be careful. You have to put it in this form.
I can't do this. So if you were 2 or 3 of this,
It's a gift around.
say,
But this is also the same thing.
60, it would be 2x minus 30, which should be to the right. Second piece is when you give it to me this way, period is 360, but when I get like this, do I do 360 divided by 2, or do I do 60 divided by, so I do it divided by this format. So it's 180.
So B,
I meant the same as 0.
is, what do we say, 2 pi over B, here. This is B. So 2 pi over 2 is the period of this guy, which is just pi.
So we do this in radians, you don't say because I have to compare it to
If you like degrees, you want to do it degrees.
We found the final.
360.
Yeah, that's how it's.
Pi over B period.
Or would this 2 should be, B should be in degrees too then? Is that what you're saying? That's what I'm on. B would not be in degrees, B would be an integer, right? Or
B is a number.
B is a number, okay.
X is either in radians or degrees. So the units are on here.
So if I get it like this, it would be that's the Trinac, and then no, this is pi over 3.
Well, this is, again, it's just, what is your, You know, I know this is confusing. There's two different ways to look.
One on the side.
Degrees, radius. Right? So the problem in degrees is 3 sine 2x minus 6. Right? So the period is 180 degrees, and the offset is 60 degrees. But the same problem would be sine
Right?
Oh,
Because secant is one of our cosine.
So if I wrote it in radians, it's all sine 2x minus pi over 3,
I think this actually might be a.
which is
Yeah, because
2 times x minus pi over 6.
so secant is one of our cosine.
So here it is pi, which is the same as 180.
This I
And C is pi over 6, which is the same as 33.
Okay, so now I realized if I got automatic this number, okay, then this is already C.
Then you say 7x minus 1.
Oh, I always do that. I thought this is to go. This is English to go?
Yeah.
So that's not C. Well, wait, you're confusing two things, right? It's not sine of 7x minus 7. The problem you're showing is the sine of 7x minus 1. So B here is 7, but C is not 1. We have to write it this way. Well, these two are the same, right? So now I can say that's C, and that's right. But this is not, this is not the same as this. Is this making sense?
Yeah.
Well, that's smart. You're doing the easy ones first, right?
Right. Yeah.
You can cheat. Yes, that's true.
Well, you can cheat through a 0. Do you have to turn it into you or?
It's optional.
Okay.
This is a learning exercise.
Or this.
Homework, you turn in.
Yeah.
If you want to hang on to the homework, that's fine too. I can't correct it then, but
You mean like as or B for the quiz or something like that?
yes. I mean, I'll get any homework back by Thursday, and you can look at it before you take the quiz.
Yeah, I need to check up. I can have gone down because when it comes to one correction, because I can then myself.
Should be, right? You missed a day. Do you feel caught up? You are. Okay. Just checking. You're way ahead of everybody.
Yeah. So this is I got two. And I need two? I see it. And pi 1.
Does this all work on the calculator the same pretty much? Yes. And you can graph things? Okay, very good. Not too much language here, right? You need to know.
So sine is 0, 0, cosine is 0, 1.
No, but change the check. Say,
Cotangent is cosine of cosine.
say, three.
So 0,
This is
this is 0.
and
This is because 0, 0 over 1 is 1. So 6.
Yeah, look at it.
When all fail, draw. Actually, just go to always 3.
It's a good start for that.
right? You can check, but you're right, it won't. If the calculator can tell you square root of 3, then you can't use it.
The pi over 6 is always opposite of 1, right?
You doing okay?
Yeah, I just forgot. You said
Oh. Okay. There might be one like that on the quiz. Yeah. Remember, 2 pi and 360, or pi and 180, the same thing. That problem caught me out off guard. And I was like, oh, it's not 360 degrees, 365 days.
No.
Right? Are the same as 2 pi.
The third
Because we're
one,
the third one, yeah.
but it's the fourth one. So now it's our 6. 1 over 3, 13.
Did you hear what I said to England? I said, if the calculator can like figure that out for you, then you can't use it.
So 1 over, so
Which is 3 over 3.
Well, I mean,
3 over 3.
if it tells you,
Oh, what if it's 1 over? I know it's 1 over.
okay.
And then the other
Well, there are calculators as well. Exactly. Exactly.
What do you
This is good.
Currently, I'm just looking over the book stuff and I was playing around with sine graphs.
Oh, okay.
Also, I'm curious, what exactly do you use Telnet for?
There's a terminal. There's a terminal into my machine.
I thought Telnet wasn't used for a long time.
It's almost every Unix-like system in the world has it.
Really?
So it's ubiquitous. It's like VI.
Oh.
They all have VI. I hate VI. I don't use it. When I use something even stupider called
Emacs.
Pico.
Oh God.
Well, you know, at least with Pico, you know what it's doing. With VI, it just kind of jumps around.
Yeah.
What mode am I in? Oh, what did that letter mean?
Emacs seemed to be relatively simple. I couldn't figure out VI at all.
I agree with you. The only problem I have with Emacs is I never seem to be able to get it to work right. So you need the right terminal emulation. Otherwise,
I never got that advanced.
well, it's like if you telnet into like a Mac, and then you telnet into like a Windows machine, and you try. They have telnet clients. but it's not as Unix-like as you want. But anyway, I'm just saying.
That's pretty ancient, isn't it? Like, wasn't it one of the first?
Yes, it's very ancient. In fact, I remember this friend of mine at university a long time ago showing me, look what I can do. I can telnet it to this machine, and from here I can telnet it to the next machine. This was like 30 years ago at least.
Is that kind of like SSH or something?
SSH is the same, effectively the same thing, except it's encrypted.
Yeah.
So if I said SSH, would you? I wonder if I can SSH in my machine.
Maybe try.
You can ask me a specific one, I can think it through. Like that one, pi over 2 for 16, sine over cosine. The cosine of pi over 2 is 0, so that's undefined. Ah, good question. So I'm not going to name names. It's one of the advanced students. By that I mean someone not afraid to ask questions. Asked a question. He said, where's the cosecant button? Now there might actually be something here somewhere, like in the catalog, like it might.
Probably down the C's.
Under the C's. Oh no, I guess not.
I want to explain. You can those three others are not in.
Ooh, you know, you can just get a math education just going through here. There's cosine. We're going to learn this one. Inverse cosine. Cosh.
I've never
Cosh. That's that character on Babylon 5, right?
No, it's like a
This is called the hyperbolic cosine. We won't get to that till calculus. All right. So how do we get the cosecant and the secant and the cotangent? 1 divided by the sine of, I don't know, let's say 30. I don't think I'm in the right mode. Yeah, now I'm back in radians from degrees. Okay, so this would be the, what function would 1 over sine of 30 be? Cosecant of 30. See how I did that? Okay, if you want the cotangent, just 1 over the tangent. Try that. Okay, everybody good with that?
Mr. Schoenbrun. I have a TI-83 question.
Not a bad teacher.
Huh?
I mean, we're down to 16 students. I don't know how to interpret that. In high school, I'd be terrible. I'd be run out of town. But I know.
There's one that the whole class might have, actually. How do you do a modulus operation for a remainder in TI-80?
I don't know. I'll take a look. Oh, well, okay, there's the, where are we? Yes, there's the question is, how do you do a modulus on this guy? And there's the brute force method. Let's say you want to say, I don't know, 83.2 mod 2.56, right? Oh. Okay, let's say A. Oh, you don't really do that with decimal numbers. Let's say I want to deal with integers, and I want to say 44 divided by 20, so that's 2 plus remainder 4. Okay? So if I have some problem and I don't care about this, I just want the remainder. Is that what you're asking?
Yeah.
How would I get the remainder? That's what you call it, the modulus. Because another way of stating this is 44 mod 20 equals 4. It's okay if you don't know this. It has nothing to do with trigonometry. It's good to know this. So the way I always do it on the calculator, I don't know, there may be a function, but what I would do is I would just say, well, 44 divided by 20. Oh, that's 2.2. Well, I just round it. So I say 20, I'd say 44 minus 20 times 2. And I would give it to you. I mean, you know, with bigger, uglier numbers that are harder to deal with. Now, is there a modulus function? Let's take a look.
Another question might be, is there a way to skip alphabetically in the catalog?
I think there is, actually. I think you have to.
Yeah, there is. You could do alpha.
Alpha. No, it's green. Oh, yes, alpha. Sorry. This is alpha. Where's M? That didn't work. I don't know how to do it. I'm sure there's a way. You know, when these things first came out, one of the mod box plot, well, I guess it's not called mod. You know, you can write a little program in here. Where is that?
You can write all kinds of little programs in here. You can write one to
Program, exact. Yeah, you can do this stuff.
program, edit, you can make your
And-
execute it.
And once you type it in, it remembers it until the battery goes dead. But, and I don't know if anyone's noticed, oh, there used to be a little connector in here. Oh yeah, the I/O port. But now they also have, looks like a little USB port. So you can actually load these things up, and it's a whole little programming world, and I do programming for a living, and I just couldn't, you know, it's like, oh, just so painful and such a bad environment. But you can learn to do it. You can actually have little video games and stuff. I used to program in BASIC on a teletype. It was the same idea. You know. I didn't say that, but I did. I have, yes. I do a lot of assembly, yeah. I said I program in BASIC. Now there's something called BAL. Heard of BAL? Stands for Basic Assembly Language. That was IBM 360 BAL. Yes, that was assembly. I've done x86 assembly. I did that Motorola M68 or something, 20 assembly. You may. We can go over it on Thursday. They're trickling out here. Okay.